All right, well, welcome everybody to our calculus notes for section 4.1 on antiderivatives and indefinite integrals. They're the same things, actually. But suppose we do the reverse of differentiation. Given a function, we find another function whose derivative is the given function. Okay, so we spent first semester taking the derivative of functions, going in that one direction. Here's a function, find its slope, find its derivative. Anti-differentiation is going backwards. So it's part of the larger process called integration. And integration is the main topic of this chapter and is actually the second branch of calculus. And the first was differentiation. So the two together kind of form this one unit we know as calculus. So we'll see that integration can be used to find the area under a curve over a closed interval, which has a ton of important applications. So anti-differentiation is the process of differentiation in reverse. It's almost like an inverse function. So if we're given a function f at x, we determine another function, now we're going to call that capital F at x, such that the derivative of capital F at x is f at x. So notation-wise, this is kind of what we're looking at right here. So what we kind of say then is that this capital F at x is the antiderivative of the lowercase f at x, because its derivative is f at x. For example, let f at x equal 2x. Well, the function capital F at x equals x squared is an antiderivative of f at x since, well, what's the derivative of x squared? 2x. So x squared is an antiderivative of 2x. However, other functions also have a derivative of 2x. Here's a couple examples. X squared plus 1, derivative is 2x. X squared minus 2, the derivative is 2x. X squared plus 2, the derivative, also 2x. So all of these differentiate to 2x, therefore they're all considered antiderivatives of 2x, right? The x squared part will differentiate to 2x, with the power out in front times what's there, knock the power down 1. And the constant term differentiates to 0. So that's why when we look at this plus 1, the minus 2, and the plus 2, they don't actually impact the derivative. And so it's always going to differentiate to 0. Therefore, an antiderivative of f at x equals 2x is any function that can be written in the form x squared plus c, where c is some constant. So that c value can be any constant. And it leads us to the following theorem definition of our antiderivative. And it's kind of just summing up everything we just talked about. So the antiderivative of f at x is the set of functions, capital F at x plus c, such that the derivative of capital F at x plus c equals f at x. And what we do is we call that constant c the constant of integration. So when we integrate, we've got to have that constant in there. Now, you can kind of look at what happens with all these functions. So all of these are antiderivatives. And notice they're exactly the same curve. They all have the same slope. They're just shifted vertically up and down. And so when you get an antiderivative, you can't actually tell which one of those you're talking about unless you have a specific point on the original function, which we'll get into later. So let's try some of this here. Let's see if we can find an antiderivative, capital F at x, of the function f at x equals 3x squared. And another way to think of this is to say 3x squared is the derivative of what function? Okay, so we're trying to look for what that function might be. So you just kind of have to think about it a little bit, and you got to think going backwards. So we have to think, well, 3x squared is the derivative of what function? Well, we know we always knock the power down 1, right? So if we're going to go backwards, well, let's increase that power up by 1. So we know the original function had to be some sort of x cubed function. Now let's deal with that constant multiple. So we do know that when you take the derivative, you move the power out in front and times what's there. And we need to make sure that what's there ends up being 3. So if we just move that power of 3 out in front, well, it looks like this will work okay. Now, you can always check this, of course, because the derivative of that capital F at x should equal f at x, right? That's how you show that capital F at x is an antiderivative. And so the derivative with respect to x of x cubed is indeed 3x squared, and so that works. Okay. Now, we just found an antiderivative, and what we want to make sure that we do now is to account for that constant of integration. So you always have to have that plus c right there. Okay. So here's another way we can word this. A differential equation, it's kind of a new term, but a differential equation is any equation that involves x, y, and the derivative of y. So you have to have some derivative in there. And if the derivative is in your equation, we call it a differential equation. Now, the solution to the differential equation is the antiderivative, or basically what is the y function. Okay, so you might see the wording like this. Give the general solution of the differential equation y prime equals 3. Okay, so we know this is a differential equation because it says y prime. So we have the derivative of y, and that's really the important part. And so what we're looking for now is the antiderivative. Okay. And so we're trying to find y. And we think, well, 3 is the derivative of what function? Well, it's going to be 3x, right? Because the derivative of 3x is 3. And we also can have some sort of constant in there that we won't really know what it is. But it does differentiate to nothing. All right. So if we're kind of lost or confused a little bit at this point, that's okay. There's a lot of new notation in here, but it'll get easier. So we start using these words a little bit. And I did want to just show a different way to think about it, maybe one that's not with so many words, but we're basically going to just go over the same concept here. So basically what we did in first semester is we said we had f at x equals x squared. Okay. Now we worked on taking the derivative of that, which we called f prime at x, and we had the power rule, so we can move the power out front times what's there, knock the power down 1. All right. Well, that is what we were calling differentiation. Okay, differentiation. And what we're going to do today is basically figure out, is there a way that we can undo the derivative or go back the other way? And we call that anti-differentiation. So we can see the relationship between those two things there. Okay. Now we might also see it with the y's, right? So y equals x squared. And if we take d over dx of y, we would get 2x. Okay, so that's taking the derivative. And we want to do the antiderivative. And so the idea is, what symbol are we going to use to tell us that we are indeed taking the antiderivative? Okay, and what we want to do and what we want to think about is if dy over dx is equal to 2x. Remember, when we're solving these differential equations, what we're really looking for is, what was that y? What was that original function? So we want to isolate y. So the first thing we can do here is multiply by dx. And if you remember, dx was that tiny little part of x that was shrinking down to nothing. And so then we'd be left with dy equals 2x dx. Now we want to get y by itself. Well, we're not going to divide by d because d is not really multiplying. More, it's telling what to do, right? And we actually have this inverse operation called integration. And we use this integral sign to undo the derivative. Okay, so it's totally new notation for you. That integral sign undoes the derivative. Okay. On a side note, it's much like a square root symbol undoing an x squared, right? And so that's kind of what we're thinking about here. So that integral symbol undoes it, and then you're left with y equals integral of 2x dx. Okay, and as we just said before, this is x squared plus c. All right. So if we think about our function notation, okay, that's where we get the integral of f prime at x dx would just be capital F at x plus c. Not capital, just regular f at x plus c. All right, so this idea of finding the antiderivative, it's helpful to use that word because we know what the derivative is. But really what this is called is indefinite integration. Okay, indefinite integration is what we're really doing here. So the antiderivative is the same thing as the indefinite integral. Okay, and this is the solution to that differential equation. Now, anti-differentiation is the same as indefinite integration. It's the process of finding all the solutions to that differential equation. And we think of integration as being the inverse of differentiation. So the notation when we were differentiating went down this way, right? And usually we just started here with f, and then we went to f prime, and then f double prime, f triple prime, so on and so forth. Integrating, it's going to go back the other way. And so that's why at the very beginning, we kind of started here at f, and we found the antiderivative and called that capital F. All right, so really it can work along any one of these notations here. So the next box just talks about antiderivative or integral notation. And we say this is the antiderivative of f at x with respect to x. And that's how you read this right here, the antiderivative of f at x with respect to x. So we have our integral sign here. We call the part that we're finding the antiderivative for the integrand, and we know this as being the derivative of some other function. And then dx is your variable of integration. Okay, so with respect to. And the solution that comes out, you have your general antiderivative plus your constant of integration forms the entire indefinite integral. So let's go ahead and try this using our power rule for derivatives. Okay, so we don't want to just kind of guess at this every time. So if we remember what that power rule was, we have ax to the nth power. Dy over dx, we would move the power out in front, right? We would times what's there, and then we would knock that power down 1. And so we're going to use that to kind of help us figure out a general rule for doing this every time. So let's look at 2x to the third. Okay, that 2x to the third right there, remember, is the derivative. And we're trying to find which function gives us that derivative. So 2x cubed is the derivative of what function? And so when I look at this, this is my dy over dx. So dy over dx equals 2x cubed. And we know generally in the power rule, that's what this is equal to. Okay, so I'm going to set that equal to the 2x cubed equal to n times a x to the n minus 1. We're just going to try to solve for a few things here. So we actually get two equations that we have here. We know that 2 has to equal n times a. Okay. And we also know that 3 has to equal n minus 1. So we have two equations, both of them are true. It looks like we can solve for n by adding 1. So we know that n has to equal 4. Well, if n equals 4, then we should be able to find a, right? We would say 2 equals 4a. And so we end up dividing by 4, which was n. All right. Now this would give us 1/2. And then see how it works. If we're going to go backwards, our derivative was n times a to the x to the n minus 1. Then the original function had to have been ax to the n. Well, now we know what a is, and we know what n is. Okay. So our integral or antiderivative is going to be 1/2 x to the 4th plus c, because we don't know what it is, and it could really be anything. Okay. Now, maybe that's felt like a tedious process, setting it equal to the derivative, working backwards, all that stuff. But it actually happens generally like that every single time. And so what we're going to do is get our power rule for integration now. And so any power function, we're going to have an antiderivative of a x to the n plus 1 over n plus 1. And then, of course, plus c. So basically, you're always going to raise the power by 1, then divide by the new power. And that is the power rule for integration. Now, we'll make one note here. What n cannot equal, this doesn't work in every situation. N cannot equal -1, sorry. N cannot equal -1. Because you would see then we would get ax to the 0 over 0 indeterminate form, not going to work. So we'll look at that example a little bit later. All right, so a couple other properties that we're getting here. If we try to integrate 0, we think 0 is the derivative of what function? Well, the 0 is going to be the derivative of a constant. If we have the antiderivative of k just being a constant, the function that gives us that would be kx plus c. So that constant multiple is the derivative of kx plus c. Now, if you do have a constant multiple times a function, it turns out that you can move that constant multiple outside of the integral. And that's going to be extremely important, as we are going to get some functions that we actually have to manipulate with multiplication. And so it's really important to be able to do that. And then a sum and difference rule. So if we're adding two functions together in our integrand, it turns out that we could just integrate those separately. Now, it turns out there's no simple rule for the product of two functions in your integral or the quotient of two functions. So we don't really have a product rule or a quotient rule for integrals. There are some techniques we can use to help find those, but we're going to discuss those more later. So let's go ahead and practice this here just a little bit. So we want to find each indefinite integral and then check our answer by differentiation. All right. So we have the antiderivative of 4 with respect to x. Okay. So when you just have a constant in there, this is going to become 4x and then plus c. Okay. Now, they did say you can always check your result by differentiation. So basically what we're saying is the derivative of the antiderivative, okay, has to be the derivative of the antiderivative. Okay. So if we basically take the derivative of both sides, the derivative undoes the integral, and we're just left with 4 on the left-hand side. And then on the right-hand side, notice what we have. The derivative of 4x plus c is 4. So it all checks out. Now, number 2 can be a little bit tricky, because all I see is an antiderivative symbol, an integral sign, and then dx. So what, in this case, is the integrand? Well, if you just have nothing in there, you don't have nothing. You actually have a 1 in there. So this would be like 1 dx. So it gets a little confusing, But if that is a 1, then we know that this would have to be 1x plus c. Again, we can take the derivative of both sides. And we'd be left with 1 equals 1. And that checks. Now we're going to get good at this, so you don't always have to check by differentiation, but just know that you can always check your answer by differentiation. All right, let's give this one a try. It's the antiderivative of 5x to the 7th with respect to x. So what we have here is we're going to leave the 5. That's a constant multiple. So that is just going to hang in there. We're going to raise the power by 1 up to 8, and then we're going to divide by that new power. And then add our constant of integration. Now we can take the derivative just to make sure we did it right. And so the 8 would move out in front, times what's there. Knock the power down 1. The derivative of the constant is gone. And indeed, we're left with 5x to the 7th. Now you might also see rational functions. Like number 4 here, 4 divided by x squared dx. And the same kind of idea applies as first semester, where you always want to rewrite the integrand before using the power rule. So we need this to be in a power format, ax to the nth power. And so we're going to rewrite this just like we used to with derivatives as 4 times x to the negative 2. All right, once we do that, we are able to apply our power rule. So we'll keep the 4. We will add 1 to the exponent and divide by that new exponent. And then we have plus c. Now, I know you can do this in your head. I just wanted to show that there, just so that we remembered that we were adding 1 there. And so this would become 4x to the negative 1 over negative 1 plus c. And then we'll just rewrite our final answer as negative 4 over x plus c. All right. Well, let's go and move on. Number 5. Here we have lots of different terms being added and subtracted together. So we can really just anti-differentiate each one of those individually. So 3x to the negative 5 would become 3x to the negative 4 over negative 4. We would have minus 7x to the 4th over 4. So add 1 to the exponent, divide by the new exponent. Minus x squared over 2, add 1 to the exponent, divide by the new exponent. And then 3. So this one's weird because you're like, there's no x, there's no exponent. But if you think about 3 as being 3x to the 0 power, because x to the 0 power is 1, then the power rule makes sense, right? You add 1 to 0, and you would get x to the first, and then you divide by 1, and there you have it. Then you have plus c. Now, usually I make you move the negative exponents down, but in this case, since it started off as negative, you could just leave it negative there, and this would be fine. And of course, I probably wouldn't show the divide by 1, x to the first power. All right, we can also do this with radicals. We just need to rewrite these as fractional exponents. So this is x to the 1/2 power. And we can still use the power rule. So x to the 1/2 plus 1 would be 3/2. Now we're going to divide by that new power of 3/2. And we have plus c. In this one, I would like you to, instead of dividing by a fraction, multiply by the reciprocal of that fraction. And so this is going to become 2/3 x to the 3/2. All right, so hopefully the process is feeling a little bit natural at this point. Add one to the exponent, divide by that new exponent. If there isn't an exponent to begin with in the integrand, you have to rewrite it so that there is, and then just simplify, clean things up at the end. Now, number 7 is x squared plus 1 divided by x squared. And I said earlier, there is no quotient rule for antiderivatives, okay? So it doesn't mean you can't take the antiderivative of a quotient. Okay? We already saw in one case you could, right? 4/x², you can do that one. When it gets a little more complicated, sometimes you have to rewrite this. And this is going to be especially when you have a single term in the denominator. This is the best thing to do. When you have a single term in the denominator, what you want to do is actually divide it out. So what I mean by that is you'll have x squared divided by x squared plus 1 divided by x squared. And this is always going to be the best thing to do with that single term. Now from here, you do want to rewrite. So x squared divided by x squared is 1. And we're going to rewrite 1/x² as x to the -2. Okay, so here we can use our power rule. So 1 will become x, as the derivative of x is 1. And then x to the -2 will become x to the -1 over -1. So we added 1 to the exponent, and we divided by that new exponent. And then we have a plus c. And the last thing I would do here is move that negative exponent. So we're going to end up with -1 over x. And I guess you could just write x minus 1/x. And plus c. All right, number 8. So this is the antiderivative of 1/x dx. If we use the methods that we have been using, this would become the antiderivative of x to the -1. And you can see that when we use the power rule, this is going to fail because -1 plus 1 is 0. And then we divide by that new power, 0. Now I got to be careful that this is not actually undefined. Okay, this actually is indeterminate because just the form of it is a little bit awkward. And we're going to eventually learn that instead of using the power rule here, the antiderivative of 1/x dx is the natural log of x. Now, maybe you could have reasoned that because you've seen this before. The derivative with respect to x of ln of x is 1/x. Okay. So anytime you're taking that antiderivative, you always got to go back to the question essentially is saying that 1/x is the derivative of what function? Okay. And that would allow you to do all the trigs. I mean, anything that you took the derivative of, you can find the antiderivative of that derivative because it goes back to the original function. And so don't forget that constant of integration there. We're going to talk about this more in a later chapter. All right, so that's how to find your basic antiderivatives. And now we're going to briefly talk about initial conditions and particular solutions. So the question here, can you find the equation of a line given a point and its slope? So we're leaving the calculus world a little bit, going back to algebra. If you have a line, you know it's a line, and it has a point and a slope, can you find the equation? Well, yeah, we have point slope form, but if we just look at this form, y equals mx plus b, that's our general form for any line. Now, m in this case ends up being what? The slope. And then b is the y-intercept, right? So if you're given the slope is equal to 3, well, you know right away you can plug the 3 in for m. And if we have the point f at 1 equals -2, right? The point is actually 1 comma -2 there. So your x value is 1, then your y value is -2. And so you can actually substitute into y equals mx plus b. Right? You plug in your x, you plug in your y, and then you can solve for the b. Right? This is the process we've done when we were finding tangent line equations. And so we'd subtract 3. We would say b equals -5. And we could go back to that general equation, plug 3 in for the slope, and -5 in for b. All right. So because we know the general solution for every line is y equals mx plus b, we can determine a particular solution for the equation given an initial condition and the slope of the line. Now, what you want to think about here is what we're really saying here. And we've said it a lot. Slope is synonymous with derivative, right? Slope and derivative are the same thing. So we could really replace all these words of slope with the word derivative, and everything would work the same. And I think something that's kind of interesting is, what if we took the antiderivative of m with respect to x? So m being the slope, well, if that's a constant, then we would have what? mx plus c. Look familiar? It should look just like that mx plus b, mx plus c. So when you were asked to do this in algebra, you were actually being asked to do a calculus problem where you were given a slope, the derivative, and asked to find the particular solution to that differential equation. So anyway, in the general antiderivative now, capital F at x plus c, the constant of integration c could be of some interest in some applications. And so in such cases, if we know a point that is a solution of the antiderivative, it allows us to solve for c specifically. And that point is called that initial condition. And so here's a couple steps here. To solve any differential equation, find the particular solution that satisfies the initial condition. Another way to say that. You want to find the general solution of the differential equation. So basically integrate the slope. Then you substitute the initial condition into the general solution, solve for c, and rewrite. And of course, you can always check with a graphing calculator to make sure that the graph goes through that point. All right, so it says, find the particular solution for the equation having a derivative of capital F prime at x equals 2x plus 3. So that is our derivative. So what we want to do is actually integrate the slope, integrate the derivative. And we're going to get, let's see, 2x squared over 2 plus 3x plus c. And so basically we have x squared plus 3x plus c. Now, the goal, the idea here is that we want to be able to find that value of c. Okay? Now, we do know the initial condition is f at 1 equals -2. Oh, by the way, this is giving us our f at x, capital F at x. All right, so if we know that capital F at 1 equals -2, we can actually find that c value. So we're just going to let -2 equal, and then we're going to plug 1 into the function here. So we get 1 squared plus 3 times 1 plus c. And we're going to go ahead and solve for c there. So we have 1 plus 3 plus c. -2 is 4 plus c. And if we subtract 4, we get -6 equals c. And so we can actually take that c value and plug it back in to find capital F at x. And that's going to be x squared plus 3x plus, well, plus -6. So let's just write -6. All right, and that is your solution to the differential equation, the particular solution when f at 1 equals -2. All right, now sometimes you're given a second derivative and asked to find the solution to the differential equation. So in that case, you're going to jump from the second derivative to the first derivative to the original function. You're going to have to do this process twice. So you will need initial conditions on the derivative and the original function. Okay, so first off, we would just look for f prime at x, and that's the antiderivative of -2, which would be -2x plus c. Now we know f prime at 2 is equal to 3. So we would just say 3 equals -2x plus c. Oh, and we plug in our x value of 2 right there. Okay, so that 2 is coming from here. 3 is coming from here. So we have 3 equals -4 plus c, add 4. We get c equals 7. And so our derivative would be -2x plus 7. Now, we want to go all the way back to the original function, which would be f at x. So we would integrate now the derivative. And again, use our power rule. -2x squared over 2 plus 7x plus c. And then we have to solve for c, knowing that f at 2 equals -1. So we just say -1 equals, I'll plug 2, I said -1, I wrote -2. So -1 equals negative of 2 squared plus 7 times 2 plus c. And we'll go ahead and solve. And that c equals -11. So we will just substitute that in for c and get -x squared plus 7x minus 11. All right, so the antiderivative of a function has many applications. So for example, velocity is the derivative of a distance or position function. And inversely, the distance or position is the antiderivative of a velocity function, okay? So if information about the distance of an object at some time t is known, that gives us an initial condition that we can actually use to find a position function. So a rock is thrown directly upward with an initial velocity of 50 feet per second from an initial height of 10 feet. Initial height, there's your initial condition. Now, the velocity of this rock is modeled by the function v of t equals -32t plus 50. Okay, where t is in seconds, v is in feet per second, and t equals 0 is going to represent the moment the rock is released. So it says determine a position function as a function of time. Okay? So just remember, if you have a position function and you take the derivative of that position function, it gives you the velocity. Okay. Well, in this example, we have the velocity and are asked to find that position. So what we have to do is integrate. And so then our position function would be the antiderivative of the velocity function with respect to time. And we'd have to be able to find that plus c based on the initial condition. Okay, so that's what we're going to do. We're going to integrate the velocity. With respect to time. So we're going to get negative 32 t squared over 2 plus 50t, and then plus c, the constant of integration. Now, where was that initial condition? Because we want to be able to find that plus c. So the initial condition said there was an initial height of 10 feet. So what that really means here is that s at time 0, the position at time 0, is equal to 10. And notice that is the function that we're looking for, s at t. So if I plug 0 in for t, the answer should be 10. So 10 equals negative 16 times 0 squared plus 50 times 0 and plus c. Well, when the initial condition happens at time equals 0, that's easy because it zeroes everything else out except for the constant. And so your constant is absolutely going to be 10 in this case. And so our position function will be negative 16t squared plus 50t plus 10. Now with that, we can determine the height as well as the velocity of the rock after 3 seconds. That's just going to be s at 3 is your height. And so negative 16 times 3 squared, and then plus 150 and plus 10. So it looks like we're going to be at a height of 16 feet. And then the velocity after 3 seconds, remember that was the original equation we had, was negative 32t plus 50. So we have negative 46 there. So what that means is it's dropping, it's coming back, and it's moving 46 feet per second. Okay, so we do know it's coming down, it's on its way back down because the first derivative, the velocity, is negative. So the function's decreasing. All right, so that is antiderivatives, indefinite integration, and how to solve for c when you have an initial condition.